Welcome everyone. This is Deciphering Coroutines. So let's get started. This is me. My name is Andreas. You can find me in various places on the web. I'm one of the co-organizers of the Munich C++ user group. We are one of the biggest user groups in the world, and we're currently meeting online because of the pandemic. Yeah, if you like to, please step by to one of our meetings. Also, if you want to give a talk, maybe practice a talk, or even if it's just a lightning talk, please reach out to us. We're always happy to welcome new faces. In my day job, I currently work as a runtime engineer for Woven Planet, which is the software company spun out of Toyota. So we are writing software for automotive systems. And we're hiring. So yeah, if you want to work like maybe from Japan, then yeah, consider applying. So what is the motivation for this talk? As you probably know, coroutines as we have them in C++20 are not exactly easy. On the one hand, they allow for extremely complex transformations of control flow. But they do so through a rather arcane syntax that changes some of the fundamental rules of the language. Furthermore, they're not only hard to understand, but like if you pick them up, you might have noticed that if you are not using them regularly, then it's quite easy to forget what you've learned about them rather quickly. So that's at least what happened to me. Maybe you've made similar experiences. So the idea of this talk is to not just give an introduction to the topic, but also give it in a way that can be remembered easily later on. So the feature is way too big and too complex to introduce all at once in a single talk. So in this talk, we're only going to focus on the syntax. So this is really like the low-level technical parts, how to get coroutines running and how they work on the language level. This is also, in a way, the most boring parts about coroutines, but it's a necessary prerequisite to understand all of the more interesting stuff that happens later. So hopefully, by the end of this talk, you will be well equipped to understand all of the super exciting advanced coroutine talks, some of which you can see here later this week. So quick overview, what we're going to do today. We're going to look at some essential use cases for coroutines. We will look at what coroutines look like from a caller's perspective, and then we will actually go into a deep dive, dig down into the steps that are involved in starting a coroutine, how suspend and resume works, and then we will try to draw like a visual map of coroutine land that helps us navigating this complex feature a little bit easier, which is also what gave this talk its name. And then we will use this map to like walk through some basic interactions, like just some of the essential features that you would want to do with coroutines. So a short disclaimer up front. As I said, coroutines are extremely powerful and flexible, and for didactic reasons, I am going to simplify things in some places and ignore some of the more advanced features just to keep the explanation streamlined and make sure that it fits in the 1 hour. So please keep in mind that all the code on the slides is very much slide code. It's always meant to illustrate a specific relationship, a specific concept in a simplified way, but it should by no means be taken as a best practice for how to write good coroutine code. So with that out of the way, let's get started with the basics. So a coroutine, in the most simple terms, is just a function that can be paused in the middle. So imagine you're just executing a function from the top down, and then just at some point in between, you're going to say, OK, I'm going to hit the pause button here, going to return the control back to my caller. And then at a later point, the caller can decide to resume execution of the function and will continue right where you left off. An implication of this is that a coroutine is always stateful, unlike a function. Because in order to be able to do this suspension, you need to remember at least where you left off, like what was the line where you actually started pausing. But usually you need to remember a lot more than this, because you need to remember the entire surrounding state, like all of the local variables of the function and what their values were at the point where you paused. A consequence of this is that you really should think of the coroutine function that you're calling not as a function in the classical C++ sense, but more like a factory function that actually returns the coroutine object back to you. And then this coroutine object, that's the one that holds all the state, and that you can resume to continue the computation later on. One last thing that's important to know is that in C++20, the coroutines are stackless. That means when I go into such a suspended state, control flow is always returned to my immediate caller. So if I have multiple functions on the call stack and I want to resume all of them, then every one of these functions has to manually handle this, this suspend logic. It's not something that happens automatically for you. Unlike stackful coroutines like you might have them in some other languages. So let's look at some really basic examples. So one example that is often cited is asynchronous computation. So imagine, for example, that you have a socket library. And the most easiest way to write code with such libraries is to just use blocking calls. That's usually the most simple, straightforward code. Of course, the disadvantage is there that you lose the thread while it's waiting for the operation to complete. That's why if you care about efficiency, you usually use an asynchronous library. But as you can see here, if you compare the blocking call at the top and the asynchronous call at the bottom, in the asynchronous case, you kind of moved things around quite a bit, right? So what was the return values of the function before now becomes the parameters to the callback function that is invoked when the read operation completes. And that leads to this weird inversion of control flow, which makes it very hard to work with such asynchronous libraries in the beginning. Like, if you do it long enough, then eventually you get used to it, but there's still some mental overhead compared to the simple blocking code. So what coroutines allow you to do is basically change the asynchronous code in a way that it looks like the blocking code. So what will happen here when you call await async read is that this coroutine will get paused, control will get returned to the call of this function, then the outer logic can continue, and then as soon as the operation completes, the data becomes available, somebody is going to wake up this function, and it's just going to continue execution as it would have done in the blocking case. So there's a few things here that are not quite obvious, like, for example, who is going to wake up this function? So you're going to need like some kind of scheduler that manages all of this, all of these events about the incoming data. And of course, since like the scheduler might not wake you up on the same thread that put you to sleep, you have to be a bit careful about like what data you access after a suspension point. But still, the mental overhead of all of this is way, way lower than it was in the case with the callback-based interface. A second use case that you see often is this sort of suspended computation. The most easiest use case here is just lazy computation. So you don't start an operation right away, but instead you get back a coroutine and then you invoke the computation of the result whenever you want. Maybe provide some additional data before retrieving it. So let's start with a real simple example here. Let's say you want to compute the Fibonacci sequence. The first thing that you would probably do, the most simple way to implement this is just have a function that returns the sequence in a vector. So this naive implementation has a number of disadvantages, and you can probably think of them already. Like, for example, this function will always require O of n storage where n is like the number of Fibonacci numbers that we want to compute. So for the Fibonacci sequence, since it grows pretty fast, this is probably not going to get very big, but you can easily imagine if I have a complex computation and I'm only ever processing the numbers one by one, then like why should I have to pay for the entire storage for the whole thing? Another consequence of this is if you're dealing with an infinite range, then it becomes a lot harder to handle because you need to decide beforehand what your maximum number is until when you want to compute it. So a different way of implementing this would be like this. Instead of our function returning the range in a vector, we're just going to return a generator object. And this generator object has then a next member function. And then every call to this next member function will give us back the next number in the sequence. So this addresses all of the concerns that we had before. Now we just get like one number after the other, and we only have to store as many as we want. And if I now asked you to implement an interface like this, you could probably all do this, even if you've never heard of coroutines before. So the interesting question is here, like, is this make Fibo generator function, is that actually a coroutine? And we don't really know. That, like, it's an implementation detail, right? All we see is the interface. And that is actually the first important thing that we need to understand about coroutines. From the outside, they just look and behave like functions. And from the outside, there's no way to tell whether they're implemented with a coroutine or not. The only thing that we really need to understand as a user of this function is the interface of this return object that is marked in blue here. So that is going to be the first piece of the puzzle that we need to understand for understanding coroutines. So again, I said before that you should think of the coroutine not like a function, but like a factory function that is producing the actual coroutine. So the initial call to the coroutine function will produce this return object of the return type and hand it back to the caller. And then the interface of this type is what is going to determine what the coroutine is capable of. And the consequence of this is, since the coroutines are super flexible, you can actually do a whole lot with this return object. So if you have some coroutine code and you want to understand what it's doing, the first thing that you should look at is the return type and what its interface looks like. And you can usually understand this without understanding too much about coroutines and get a pretty good idea for what's going on there. So the only thing that the client needs to understand is this object, and there's no special rules here. It's just like any other C++ object, and the function signature, you can just read it like any other function signature. And the important thing here is that like we design this return type, right? So if you're writing a coroutine, you can decide what goes into this interface. So now the obvious question is like, what actually does determine whether a function is a coroutine? It's not its signature, right? Because like the signature, that's just like any other C++ function. So how does the compiler actually know whether the function is implementation is implementing a coroutine or not? And the answer is rather simple. The compiler just looks for one of these three keywords in the function body. If you find that, that's the distinguishing factor that makes it a coroutine. And as soon as one of these keywords appear in a function body, that drastically changes the rules for how the code inside this body works. So if you try to read it with the mindset of like a normal C++ function, then a lot of the stuff that you see in that body will not make sense anymore. So for instance, as we can see here, we have this co-return keyword, which replaces the classical return keyword that you know from C++. And if you try to use now both co-return and return, it won't compile anymore. So you cannot use the return keyword in a coroutine. So let's look at what the body of our little Fibonacci generator would look like. So as you will notice, this is very similar to what it would look like if you just wrote a loop that like printed all the numbers to the console. The only difference is that where before we would write the print statement, we now have this co-yield statement, which basically hands the number out to the caller. And we don't quite understand how this works, but just to give you an idea, like this is what an implementation would look like. And the fact that the control flow is the same as it would be for this simple loop that just printed the numbers, that's the important feature here. Because that is, again, typically the most simple control flow. And for such a simple generator, it doesn't make much of a difference, but the more complex your generators get, the more important this gets. So for those of you who have some experience with writing iterators, like if you just have to write a loop that iterates a data structure and then have to write a class that acts as an iterator, like the second problem is much harder than the first. And this is where coroutines help you. So another thing to notice here is that the function signature actually doesn't match what is happening in the body at all. Like, where is the return of the Fibo generator object? Who builds this object that is returned from this function? It doesn't appear in the body at all. So for the rest of the talk, we will try to understand what these special rules are that are applied in this body of the coroutine function. And how we can write code for this. So let's start out by trying to write the simplest possible coroutine that you could come up with. And this is the smallest one, right? It cannot be empty, because if it's empty, it's just a function. But if I just have an empty co-return statement in there, that's enough to turn it into a coroutine. So obviously, I have to implement this return type object next, so that's what I'm going to do. Again, I try to start with the simplest possible thing here, just declare an empty type. And if I try to compile this, I will get a compiler error. And the compiler is going to complain that it's looking for a nested type called promise type inside of this return type struct. So, okay, yeah, let's try and make the compiler happy. And let's define this nested type. We just provided inline here because that's the simplest way. It could also be a type def, doesn't matter. Like the compiler just has to find a type under that name somewhere. And this promise type is now the second piece of the puzzle, the second important participant in the coroutine mechanism that we need to understand. So let's take a look at that. So why do we need the promise? An analogy here that you might think of if you hear the name is futures and promises from the threading library of C++11. So with futures and promises, the future is the thing that the function hands out back to the caller, that the caller can use to retrieve the result. So the future in our terms here has the role of the return object. Right? It has a .getMember function, and that gives you the value back. But you need something that remains on the producing side, right? So in the future promise case, the function that does the asynchronous computation holds on to the promise, and that's where it puts the return value that will be given to the caller when it calls get on the future. And the idea behind the promise type for the coroutine is similar. So this is just the object that remains inside the coroutine, and that is basically like the interfacing object from this side. But don't take this analogy with the future promise too literally, because like the coroutine promises, they work differently, right? So it's not everything that you know from future promise applies here. But just to understand why it's called a promise, I think that's a good way to think about it. So unlike in the future promise case, where the promise is an object that the producer constructs on its own, for the coroutines, the promise object is something that will be generated automatically by the compiler. You don't generate this on your own. And the promise, as we will see later, is also sort of the central intersection point for the coroutine code and the caller code. One of the important functions of this type is that it determines what happens at essential points in a coroutine's lifetime. In particular, what happens at startup and completion of execution of the coroutine, and how you handle various return values when the coroutine reaches the end of its control flow. So if we're trying to implement this promise, again, if we start with an empty type, we're going to get a bunch of compile errors that the compiler expects some functions to be there. And we're just going through them very quickly, just so that you've seen them one. So the first thing that it expects is this getReturnObject function. And as you can see, the return type of this function is the same as the return type of the coroutine function. So what happens here is that the compiler implicitly calls, when the coroutine starts executing, it calls this getReturnObject function, and now it's up to the promise to construct the return object that will be handed back to the caller, right? So like in the Fibonacci generator, this Fibo generator objects, that's where it would get constructed. And then the compiler will just store that away in a magical place. You won't see that in the source code anywhere. But when the coroutine reaches its first suspension point and control flow is returned back to the caller, then the caller will receive this object as the return. The next thing that we need to specify is a return void function. And that is basically the customization point for handling what happens when we reach the co-return statement in the function body. There's also a corresponding return value if you don't have an empty co-return statement, but actually try to return a value. But since we just had an empty co-return statement, this is the one that we need. The next one is an unhandled exception. And that, similar like the return function that handles what happens when we reach a return statement, this one handles the case where we exit the coroutine through an exception. And we're just going to leave all of them empty for now. And then we're going to need to implement two more functions, initial suspend and final suspend. And these are basically the customization points that allow us to execute some code both when the coroutine first starts executing, that's the initial suspend, and in the case shortly before the coroutine ends executing for good, and that's the final suspend. So for example, if I return from a coroutine, or if the control flow falls off the end, or if I exit via an exception, that's all the cases where the final suspend will get invoked. And as you can see here, we're returning here this suspend always, which basically says, okay, at these points, I just want to go into suspension. So the typical implementations for initial suspend and final suspend is you either return suspend always, which means you pause execution at this point, hand control flow back to the caller, or you do suspend never, which basically means you just go on. You just continue executing inside the coroutine. And we don't quite understand what this suspend always and suspend never, what that is, but we will get to that in a minute. So now actually we are at the point where the coroutine compiles, and we can run this simple example here. And we can already see the suspension in action, because if I just call hello coroutine here, it will not print anything. But if I change the initial suspend function to instead of suspend always, return suspend never, then all of a sudden I see the output on the console. Right? So in the suspend always case, it just stopped executing, it just paused, and since I never resumed it, I also never saw the output on the console. Of course, I was actually leaking the memory for the coroutine here, since I also did not free it. But as I said, it's just slide code. So how does this actually now work with the coroutine suspension? How can I actually put a coroutine on pause? And for that, we need to understand one more piece of the puzzle, and that's the awaitable. And the easiest way to think of the awaitable is that this is just a type that I can call co-await on. So like co-await is like an operator. It expects some value as its argument. And like all of the types that provide like objects that make valid arguments for co-await, those are awaitables. So the way to think about the calls to the operator co-await is that these are opportunities for suspension. So these are the points, and these are the only points where the compiler can pause the coroutine and hand the control flow back to the caller at this point. The awaitable controls what happens at this point, like whether we actually go into suspension and what is the code that is being executed here. So they provide, like in similar ways as the promise provided these hooks to control what happens at startup or when we return from the coroutine. The awaitable provides these hooks for determining what happens when we go into suspension. And like they may actually decide not to suspend at all, but just continue execution, which is why I said it's just an opportunity for suspension. Not every co-await call necessarily suspends. So let's do the same thing as before. Let's just try to implement such an awaitable. And we will see again that the compiler will want us to provide a couple of functions there. The first one is await ready, and that function returns a bool. And this actually determines whether we do actually go into suspension or we just continue executing. So for example, if you think about a function that like waits for some asynchronously computed result, it might be that at the time that we get to the co-await, the result is already there. So we don't actually need to go into suspension, we can just continue executing. And in that case, we would just return true here and say, yeah, we're ready, we don't need to sleep, just go on. The next function here is await suspend, and that is the customization point that will get executed shortly before the function goes to sleep, shortly before the function goes into suspension. This one gets as its parameter a coroutine handle, which we will see in a minute what exactly that allows us to do, but just think of that like a raw pointer to the coroutine frame. So it's just a handle that allows us to somehow refer to this coroutine frame that was generated by this factory function, and that now lives like somewhere in a magical place. So you will see that the coroutine handle here, it's a template, and you can just invoke it like with the empty template brackets. Then it will just be type erased, and it can point to any coroutine. But you can also use the specialized version that is specialized on the promise type. And this is exactly the promise type that we saw before. So then now the handle is more specific. It can only point to coroutine frames that actually use this promise type. But in many cases, you know which coroutine your handle points to, and then that is usually the better thing to use. The last function here is await resume, and like await suspend is the one that gets called before the coroutine goes to sleep, and await resume similarly is a function that gets executed right before the coroutine wakes up again, right? So imagine like the coroutine was put to sleep, the caller did some other stuff, now eventually they decide to resume the coroutine, and then await resume will get called, and only after that will the execution of the function body continue. And that's already the whole awaitable. So the most simple way to implement this is to just leave await suspend and await resume empty, and have await ready just return false. So basically saying it's never ready, it always wants to go to sleep. And this is then actually the implementation of the suspend always that we saw before on the promise functions. So I promised you to take a real quick look at the coroutine handle. There's like mostly two functions that are interesting here. The first one is resume. So what resume does is simply it resumes a suspended coroutine. That's all that it does, right? It continues execution if it was paused before. Please only call it if the coroutine was actually suspended and not if it's running. And the second one is destroy. And what destroy does is like if you think of like this coroutine frame living somewhere where all of this all of the state of the execution is stored, like one way to destroy this state is to just like run to completion, just let the coroutine run to the very end, then it will just clean up after itself. But the far more common case is that you want to manage the lifetime externally, and then you can just call this destroy function, and that will just get rid of the coroutine state. It will shut it down without having to resume it. And notice that the coroutine handle is not a smart pointer type, right? So you have to call the destroy explicitly. The coroutine handle is like a raw pointer. It doesn't destroy anything on its own when it goes out of scope. There's two more functions. They're not very exciting, but basically you can convert from a coroutine handle to the promise object and vice versa. That's all that those two do. And with that, now we can actually start writing our little cheat sheet that will help us understanding coroutines and writing our own coroutine code. So I was playing around quite a lot with how to best represent this, and I was trying out like various representations like graphs and sequence diagrams and whatnot, but I actually like this one the most for two reasons. The first one is that like you can just copy paste this into your code, and that already gives you the skeleton that you would need for a coroutine implementation. And the second is like you can just read it like one line after the other, and it will give you a pretty good idea of what is actually happening like during the startup phase. So as we've seen, like the first thing that the compiler, yes, Pablo? Oh, I will get to the slash in a moment, yeah. So if we look at the first line, like the first thing that the compiler will look for once it saw like one of the three keywords and decided that this is actually a coroutine, is it will look at the return type, right? And the return type will determine what the promise type is. One thing that I didn't mention before is the promise type does not necessarily have to be a nested type def. If for some reason you cannot provide a nested type def, you can also specialize the coroutine traits template to point out where the promise type is. And that's why we see the slash here in the beginning, right? So if you don't put that information in the return type, you can also put it into the coroutine traits. Like you can write a coroutine that has return type void, for example, and that will work this way. Then once we have the promise type, the compiler will construct this promise, and the arguments passed to the promise will be the same arguments as you have on the function signature for the coroutine. Timo, you have a question? Exactly, either the one, yeah, so exactly, the slash means you do either the one or the other. Yeah, sorry if that's confusing. So yeah, the promise type gets constructed, and the constructor arguments, like you can either have a default constructor, or you can have the same arguments that you passed to the coroutine function, and then they will also be passed to the constructor here. Then the getReturnObject function will get called, and the return object that will get passed back to the caller is constructed by that. And then the initial suspend function is called, and that's it. After that, the coroutine is started, and the function body starts executing. Similarly, on shutdown, like you may either return a value if you have like a co-return something statement, or if you just fall off the end or have an empty co-return statement, then the return void will get called. And again, the slash indicates it's either one or the other. You cannot do both. Then we need the unhandled exception in case we don't exit with a return value, but with an exception. And then once the return has been processed, the final suspend is invoked. That's like the last thing that we do before the thing is shut down. Then I have a similar small sheet for the awaitable, and that just lists the three functions that we have there. And with that, we finally have seen like all of the key components in place. So we have the return type, that's the object that gets handled back to the caller. We have the promise, that's the function that provides these customization points for startup and shutdown, and that lives in this magical place generated by the compiler. We have the awaitable type, that's the one that always comes into place when I actually want to suspend, when I do a co-await call. And then we have the coroutine handle, which is like a pointer to this coroutine frame. So that was a lot of information now, and you probably still don't have a good understanding how all of this works. And that is because like we've only seen all of these objects in isolation until now. And the interesting part is now how do they actually work together? What are the connections between them? So we've seen a simple example for suspending. Now, how do we actually wake up a coroutine? How do we resume execution? So let's say, going back to our simple example from before, I do suspend always on the initial suspend. So the initial call to hello coroutine prints nothing. And now at a later point, I want to resume the coroutine. And that's the point where I want to print the console output. So the initial suspend, that's what puts the coroutine to sleep. So it goes to sleep before it starts executing anything of the body. And then only when I call the c.resume at the bottom, that's when it wakes up again and the body actually starts executing. So as we've seen before, there is a resume function on the coroutine handle. So that's obviously the one that this resume member function of the return type will need to call eventually. But how do we actually get this handle into our return object? So it's time to make some acquaintances. This is all of the objects that we've seen so far. The caller obviously knows the return type, right? Because like the return object, that's the thing that gets handed back to the caller when it calls the coroutine for the first time. So that connection is clear. Similarly, the coroutine obviously knows the awaitable, because the awaitable is the thing that appears on the together with the co-await call. So that appears in the coroutine body. And we also saw that like because of the member functions on the coroutine handle, we can convert a promise to a coroutine handle and vice versa. So with those two, it's like if you have one, you can always get to the other. Works both ways. So what we now want to do is to somehow get the return type, the blue object, somehow make that acquainted with the coroutine handle so that we can implement the resume function. And if you remember from before, like in the promise type, we had this getReturnObject function. And as you can see here now, like that gives us a connection from the return type to the promise, right? Because that's the case where that's the place where those two meet. So what I can just do is inside the getReturnObject function, I just create the coroutine handle from the promise, because remember, like those two, the handle and the promise, they are basically interchangeable. And then just pass that handle that I created as a constructor argument to the return type. And now the return type will just take this argument in its constructor and store that in a member variable, as we can see at the bottom. And now in the resume function, I simply go to this member variable and I call resume on it, and that's it. That's how I implement it. So that is the connection here. Like I will, and that is typically how it's done. Like you don't necessarily need to store the handle in the return object. In some rare cases, you also want to store it in a different place. But I would say like in the vast majority of cases, this is how it works, that the handle gets passed to the return object on construction, and then you have it in a member. So now we already have quite good connections here. How does the awaitable now come into play? And here the key is the await suspend function. Because as you might remember from before, the await suspend function takes as an argument to the call the coroutine handle to the coroutine that is about to be suspended. And that's the connection here. So in the await suspend call, the awaitable will actually get past this coroutine handle as an argument. And this is something that gets generated by the compiler, right? So we don't have to worry about it. And then you again see like on the left the connection between return type and promise to get return object. And with this, we now have all of the pieces connected, and now we can actually start writing some interesting code here. So the simplest thing is let's just try to get some data out of the coroutine. Like we saw in the generator example before, I want the coroutine to produce some data, and then I want the caller to be able to access that in some way. So how does that work? So we start inside the coroutine. That's where we want to produce the value. The only thing that the coroutine has access to is the awaitable. So this is what it would look like for the coroutine, right? So I just do co-await on some awaitable, which I call the answer here. And 42, that's the value that I want to pass out. And like again, the awaitable is just an object like any other, right? So the only way that I can pass data into that is through the constructor. So just on the constructor of the answer, I will take the value and store that inside a member variable of the awaitable. So now my data lives in the awaitable. The next step from there is through the await suspend call, I can get the coroutine handle and eventually to the promise. So now in the promise, I also add a member variable for storing the data. And on the await suspend call, I take the handle, which is passed to me as a parameter. From the handle, I can get to the promise. And then I just access the member variable in the promise and store the data there, right? This is just like writing to a member variable. Nothing special about this. And now the data lives in the promise. And that's the place where we want it to be. Because as I said before, the promise is the central intersection point. That's where both sides meet. So now we're going to go from the other side. Like our coroutine has gone to sleep, the value is stored in the promise, and now we're going to access it from the caller side through the return type. So this is how it's going to look like on the caller side. I'm going to call the coroutine, and then the return object that's handled back to me has this getAnswerMember function, and that will return me the value that was stored by the coroutine before. And as we said before, like we have stored the coroutine handle when we constructed the return object. So now to implement the getAnswer function, we just use this handle, get a reference to the promise from the handle, because the two are interchangeable, and the promise has the data. So we just copy the data out of the promise, return it back to the caller, and that's it. That gets the answer out of there. Now let's try the other way. I want to get data into a coroutine. So the caller puts the coroutine to sleep at some point and then wants to provide some additional data so that when the coroutine wakes up, the data that the caller put in there, it can actually access it. So again, the promise is the central point of intersection here. And the way from the caller side is the same as before. We have to go through the return object and through the handle. So this is what it would look like on the caller side. So I have a coroutine, it gets created, then eventually it suspends. Control is returned back to main, and now main provides the value 42 as the additional data. And inside the coroutine, on the top, so the co-await call, that's what puts the coroutine to sleep, right? So it reaches the co-await call, then control flow goes back to main. Main calls provide 42, and that will wake up the coroutine. It will resume execution right at the co-await call, and now the return value that falls out of the co-await call, that is going to be the 42 that we put in there in the main function. So writing the provide member function, that's pretty straightforward. Again, we're on the return object. The return object has the coroutine handle, and we just use the coroutine handle to store the value inside the promise. And then the data lives in the promise. And the one additional thing that we also do here is I call resume on the handle so that it continues executing right away. So data is in the promise. How do we get to there? Again, like the other path is we have to go through the awaitable. So on the await suspend function, that's the place where the awaitable gets to know the coroutine handle. But the await suspend call, at that point, the data has not been provided, right? The coroutine is just going to sleep, and the data is only going to be provided later on by the caller once I've already gone to sleep. So I cannot do anything inside the await suspend function except just store the handle for later, but I cannot access the data here because it's not there yet. But in the await resume call, that's the one that gets executed right before the coroutine continues execution, right? So that's like the caller has just stored the value in the promise and has called resume on the handle. And now I wake up in here, and now I just retrieve the data from the promise. And notice here that I changed the return value of the await resume call to be like the same return type as the value that I want the co-await call to return. So the await resume here, that's actually how the data that was put into the awaitable gets out back into the coroutine. And that completes the picture. So if we think back to our example from the beginning, where we wrote this coroutine, this Fibonacci generator function, we can now already implement this with coroutines. It will probably look something like this, and it's the case of like passing data out of the coroutine. So I need to write an awaitable. I hand all of the numbers to the awaitable, and then the caller can retrieve it from there. But what we actually want to write is this. So it's functionally equivalent to what we saw before, but instead of having to spell out this weird awaitable name, I just want to be able to say co-yield, and then the compiler should just know how to interpret this. So this is really just syntactic sugar for what we saw before. Yeah, how can we actually make this work? And there's a special member function for that we need to implement. It's an additional function on the promise. We only need to implement that if we actually want to support this co-yield syntax. And it looks like this. So the member function is called yield value, takes as an argument the value that was passed to the co-yield operator, and then it returns the awaitable that will then be awaited on, right? So if you understood co-await, then you can always think of co-yield as just syntactic sugar that allows you to not having to spell out the type of the awaitable. But if you think about this a little bit, then you might actually notice that this is now actually a pretty convoluted way of doing it. Because inside the yield value function, we are already in the promise. So instead of going through the awaitable, I can just store it in the promise right away. So I write it to the member variable in the promise right away without going through the awaitable first. And then the awaitable that I return is just suspend always, which just says, okay, I'm done, put me to sleep. So in this sense, the yield value it's like a shortcut, right? If I do co-yield, then I don't have to do this dance going through the awaitable and through the await suspend function. I can just store the data directly into the promise, and that simplifies things a bit. Then there's one last thing that I want to show you today, and that is symmetric transfer. So sometimes usually when I do a co-await, I hand control flow back to my caller, right? So in the initial case when the coroutine just started, that is really the function that called the coroutine function in the first place. And in the other cases where I was resumed, then whoever called the resume, that's the one that where the control flow gets handed back to. But what I can also do, which is quite useful in a number of cases, instead of handing the control back to the caller, I can hand control back to another coroutine. So if you imagine you have two coroutines, both of them are suspended. Now you wake the one coroutine up, and then when that coroutine goes into suspension, instead of handing control back to the caller that resumed the execution on that coroutine, you instead hand the control over to the other coroutine, and then that continues execution. And this is implemented like a tail call, so like the two really switch places on the call stack. It's like not that you have both coroutines on the call stack, it's really the one disappears and the other takes its place on the call stack. And implementing this is quite straightforward. You just take the await suspend function that we've seen before, and instead of returning void, you can return a coroutine handle there. And then when you go to sleep, what will happen is that we'll wake up this coroutine that this handle points to. So this is a bit convoluted now because we're now talking about two different coroutines. So the await suspend gets passed as an argument, the handle to the coroutine that is about to go to sleep. That's why I called it me. And now the awaitable would need to get passed as a parameter or have by some other means access to another coroutine handle of an already suspended coroutine that we want to hand control flow over to. So I would need to store this other handle somewhere. And then in the await suspend function, I can just say, okay, if there is a handle stored somewhere, then that's the coroutine that I want to wake up. And in the other case, I'm just going to wake up myself again. That will be one way to implement it. Yeah, but really, I mean, the only thing that is important here is you just change the return value of the await suspend function to a coroutine handle, and that allows you to get access to this pretty powerful mechanism. And that's it. That is really all the syntax that you need. And like the two use cases that we saw for passing data, that's really the essentials. Everything else follows from this. If you've understood this, if you can do this, then you can also understand pretty much any other coroutine that we've seen. There are some cases in which the constructs are a little more difficult. Like, for example, in our case, we always had like the return type, the promise type, and the awaitable be distinct object types. Sometimes you can have, like, for example, a type that is both return type and awaitable at the same time. That's where things get interested. But as I said, we're only going to do the boring parts here today. And the more interesting things go to another talk for that. Learning the syntax was also the easy part, right? It's a lot of things that are up in the air at the same time that you need to keep in your head. But really, the mechanism is quite straightforward. It just like goes through a few functions. invokes the customization points at the right times, but that's it. What that allows you to do in terms of manipulating the control flow, that is where things get really challenging, but that's also where things get fun. So I encourage you to like use this, what you've seen here today, and just start playing around with this. Just see what interesting examples you can write there. Designing libraries that are built around like this kind of asynchronous control flow is a very deep topic, and I really hope that we will see many more talks about that in the future, because it's really exciting. Like you can do really powerful stuff there, and it's kind of mind-boggling what you can do to control flow with this mechanism with comparatively little code. So for now, I think like the main takeaway that I want to leave you with is like the cheat sheet that I hope will help you like retain this knowledge and help you if you try to play around with coroutines on your own. So we have the start-stop, we have the awaitable, and then what I think is the real moneymaker here is like this map that shows you how everything is connected together. Some references for you if you want to read more. As I said, like the interesting stuff we didn't get to in this talk, but these are some of the places where you can continue looking. And here you have a little QR code if you want to download. I compiled like a single PDF that contains all of the stuff that goes onto the sheet, onto the cheat sheet. Thank you. We still have 3 minutes left for questions, if people have any. Yes, please.
Did you say earlier that I think when you were talking about the coroutine traits, that you could have a coroutine return void?
Okay, so the question is, I mentioned when talking about the coroutine traits that you could have a coroutine returning void. And yes, you can do that. So you have to be a bit careful because like when you just return void, the caller has nothing to hold on to. So you probably want to like save the handle to the coroutine in like some other way, which you can, I mean, you can do that, right? There's ways to save data other than the return value. But yeah, you can totally do that. Like I said, it's a very flexible mechanism. It allows you to do a lot of stuff, not always sensible. Yeah, right. You could potentially use that to have like a fire and forget mechanism that just launches it and then I don't know, maybe hand it off to a scheduler that then manages it, or not look at it at all and pray for the best. Yeah. Yes.
In one of the example functions, the final suspend was no except, but the others were not. Is there a specific reason final?
Final suspend needs to be no except. That was a typo. The compiler will complain if it's not no except.
Okay, thank you.
Yeah. All right. Yeah, Timo.
Yeah. Not really a question, but could we see the slide of the QR code again because it was on screen for like 2 seconds?
Oh yeah, it's already here. If you can put it back on the projector, then otherwise you can.
Thank you.
There it is. Yeah, thank you so much.
All right, thank you for the talk. We have a couple of questions online.
Okay, cool.
First one from Rohit. Does the compiler need to know when compiling an application that depends on library functions which internally utilize coroutines?
Well, so only the compiler that is compiling the coroutine. The compiler, so if you have two translation units, right, like the one has the implementation of the coroutine, the other is just a caller that just calls it, then only the part that compiles the implementation needs to know about coroutines. The other part, in the extreme case, it could just be a C source file, right, that doesn't know anything about C++. As long as it can understand the interface of the coroutine function and what the interface of the return type is, that is enough. But it does not need to know anything about coroutines.
Thank you. Next one. What do initial suspend and final suspend permit that would not be possible using only the constructor or destructor of the promise type?
Yeah, so in the constructor of the promise type, you cannot co-await, because the constructor is just a normal function, it's a constructor function, and you cannot co-await in that because co-await only works in coroutines. So in the constructor, I mean, yeah, theoretically you could have like some other mechanism that allows you to say, I want to go to sleep after executing the constructor, but that would also need to be its own mechanism, right? And with, yeah, the final suspend function is so like you would need some special mechanism. You could not just do it with a normal constructor. And similarly for the final suspend, there's just, I mean, the final suspend, yeah, there's just no way where you could do the co-await in your own source code. It's because it happens after the return value was already processed that you go into suspension there. Yeah.
Thank you. How will coroutines work with something like executors?
That's a great topic for another talk.
Fair, thank you. Looks like you used LaTeX for your slides. I love it. What font did you use for your code?
Oh, what fun. I just used the LST listings package. I don't think I customized the font for that one.
I think the other people answering that question had the right answer there as well.
Great.
They were answering in line. Last question. Does await resume get called even when await ready returns true?
No.
Thank you.
Thank you. Thank you. Oh, yeah, one more.
One quick question. You mentioned that the coroutine handler, it can be destroyed using the destroy function or when it runs to completion.
Yeah.
Is there a clean way of checking if it has run to completion? No.
That's why, like, you should really always suspend always on the final suspend and destroy through the coroutine handle. That's usually the right answer. There's some very rare use cases where you don't want to do that, but yeah, just that's the cleanest way of doing it.
Wonderful. And also, when when the resource is freed for that promise and whatnot, does it help? Does it automatically clean up the awaitable object as well?
Yes.
It does. Okay.
Yeah.
Thank you.
Okay. Thank you, everyone.